Okay, so for the workshop, basically,
Are you running 34.2 yet?
you can run 34.2 or 35.8 should be okay also. It's mostly for the C# plug, like all other 35 were quite painful, but 35.8 should be fine. So what I'll do for the workshop, there's not too much you will do yourself. So compared to last node format, idea is to, like, every patch is ready to go basically. So there's no incomplete patch anymore. So every patch is ready to go, is working, so you can already play with it. And basically I will explain how it works, because trying to make everyone follow at the same time takes too much time. So this one will be a bit more like everything's ready and I will spend time to explain. And I'll probably change the patches around to show new things. So what I'll do, I'll post latest version I have as a contrib on the same page. So you can have the initial version, which is already there. And you'll have the final version with the other examples I've done.
Evil tweet engine's trending.
Yeah.
Get it, bro.
So to start, well, we'll start quite easy. So what I'll go through is I'll go a bit through blend state, because it's well, so it's not about XLSL, but this one, well, blend state can do quite a lot, and they're a bit underrated sometimes. So to see blend state, we'll have. So yeah, idea is you have a patch which has advanced version of blends, and you have a grid with different modes, so you can so it's possible to see a bit what it does. So you can change blend alpha value for the source and the destination. So idea with blend is you have a few pins around, so you have the render state in. That one we will not go through. We will go through operation mostly, alpha operation, source alpha, and destination alpha. And write mask. So idea of blend is like simple operation which runs after pixel shader. So once your pixel shader completes, then the unit is sent to the blend. But actually on the graphics card, the blend stage and the pixel shader are generally compiled together. So in DirectX11, you have a separate view for your blend state and for your pixel shader, but in theory, normally nowadays on the card, both of them are compiled as one unit, so the blend code runs as some form of post-pixel shader, but it's one single unit most of the time. So what the blend mode does, it does a simple operation. I'll just write it here. As I said, I will put that one in contrib, so you don't need to type this also. So what it will do, it will run this operation, so operation, which you have different choices. So you have add, subtract, reverse, subtract, minimum, and maximum. So you have this destination alpha blend, so it's always a bit confusing because destination is actually what's already in the render target. So it's what you will write, but it's already what's already in there. So source and destination are often quite confusing. So it will take the value of what's in the render target multiplied by this operator, which is destination alpha blend. So for example, if you put 0, it means it will not, it's destination blend. So for the color component RGB, it will take what's in destination, multiply by the color inside the render target. then it will perform the operation, and source blend is a new color which is just out from your pixel shader. So basically, if you have green in your render target, just plain green, and you output plain red. If you have 0, that means you will put 0 green, so you will completely ignore what's already in the target. If you put 0, for example, in source blend, that means you will completely ignore what you wrote from your constant. So you can see them a bit as grid here. So and so source blend, destination blend applies those for RGB, and source alpha blend and destination alpha blend applies that for alpha component. And then write mask tells where you want to write. So you can also say suddenly to your blend unit, I want to only write red. No. Or you can say I want to write nothing as well, which so it will perform render target dot RGB multiplied by destination blend operation, and it's pixel shader out dot RGB multiplied by source blend. And for the alpha, it's exactly the same operation, but it's applied for the alpha channel. The only exception in that case, because there's always exceptions, is it's always operation except minimum and maximum. Like minimum and maximum will always ignore the source and destination blends. So if you put operation here maximum, you can see whatever source blend or destination blend I have, everything is the same because it takes maximum everywhere. And minimum obviously does the minimum operation and ignores as well. So if we go back to add, so if we check the operations, so yeah, we have 0, which basically means, well, we'll just completely ignore because it's a multiplication. 1 will mean take the full value. Source color will mean take the multiply by the color of the pixel shader output. Inverse source color will be 1 minus. Source alpha is source alpha. So source is always out from pixel shader. So that source and inverse source will be alpha value from pixel shader. Destination alpha inverse will be what's alpha in the render target. Destination color, inverse destination color is RGB. Blend factor is a special one. I'll show it in another patch. I'll use the other patch to demonstrate the examples after, because the grid is good for overview, but to show specific one, like they also depend on some other value. So blend factor are a bit special, and secondary source color is a bit special. We'll not really go through that because it's not very useful. So blend factor is actually a special value which is outside of the shader. So you have, if you check here, you have the node blend factor render state, which is a color value. And actually, instead of using an output from pixel shader or from render target, you can also use this blend factor, which is a color which is user provided outside. So we'll go through, I'll take blend factor and I'll do state examples. So this one will be example of blend factor. What I'll do, I'll copy a few of those render state and I'll make few examples which are, let's say, so what we'll do, like if we want to do standard alpha blending, that's our alpha value here, alpha 1, alpha 2. And So here we have, well, we do, so for example, blend factor is a special value, so we can use it from this node here. So that means sometimes you can't always touch your pixel shader for some reason to apply alpha, for example, so you can use this separate value. One thing with blend factor, it's also per channel, so if you just split completely, you can say you can blend the red channel with 0, so you can say I want to keep 0. So instead of writing this with a custom pixel shader all the time, blend factor allows you to do it directly in patch, so you can do quite a bit without always going to clone constant and do something. Sometimes it's a bit cumbersome, so states can do quite a lot of operations. So for example, you can say here I want full green and full blue from 1. And operation add, of course. So I'll copy that one here. Ignore that one. Yeah. That's source alpha. Yes. So if we get for like, so we'll go through, so that, for example, that will be the standard alpha blending. So when you take blend in the presets list, like this one will exactly be alpha blend. So what it does, it will say, take the alpha of the value outside of your pixel shader, which here is 1, for example, and add 1 minus this from the render target. So that means it will, in the case alpha is 1, it means takes only full color. But what you can do, for example, instead, if you want to use the alpha, which is stored in the first constant, you can already reverse that. So I'll just write here alpha blend. So now instead you can say source destinations alpha inverse. So destination alpha and inverse destination alpha. So in that case, instead of taking the alpha which comes out of the pixel shader, we take the alpha which is already in the render target. So in that case, instead of using, we can blend using what was previously in alpha. So in some case, when you do custom blending, sometimes it's quite useful because your alpha is bound in the first texture, so you want to use that value instead. So you can also do this type of thing. You can choose, or I can alpha blend. It's like reversing alpha blend. So now alpha here does nothing, obviously. So that one is alpha blend using alpha in first in existing target. So that ones are one of the most, well, common, of course. So blend, like other one, you already have them in the preset. But yeah, for blending, sometimes also needs subtraction, so it's already part of state. So yeah, you need to remember you can use some of those also. Like sometimes I've seen plenty of time people do custom shader for subtracting. You can just use subtract in the blend. That's kind of much simpler. And you can have, like, for example, you can keep that case, which is a bit situational, but there's a few times where it's wanted. You can do a 0. 0, 1 will basically, sometimes it's, if you want to say, I really want to write to depth only, for example, in some cases this one is useful. You can set source blend to 0, so that means you completely ignore what you're writing, but you still write in depth buffer or stencil. So when you do depth buffer or stencil only rendering, sometimes you still have your color buffer which is around, so you can also completely disable write like that. So this one disable.
Is it faster if you disable it then?
Well, it's normally it's slower, but it's in case you don't have choice. Sometimes you don't have choice, so you have to do slow version. If you can, ideally you should do read only depth and don't write to color at all, of course. But sometimes it's not straightforward, so no write. So you can do a no write this way, or you can do a no write also with whatever and put a write mask to none. That's also one option. I'm not sure which one is the fastest on the card actually, but it's quite still situational. So if someone wants more blend question or anything, maybe. Otherwise, I'll maybe go to the next one. Okay, so I'll go through next. Okay, I'll go quickly again into, so who never wrote a geometry shader? I guess that's a bit quicker. Okay, so that's good that I have a bit of introduction again, quick. So yeah, I'll go quite through. Okay, so I'll just really do quick intro again for people who not too used to it. So when you go through stages, you have, well, it will be a bit of repeat for some people, I know. So when you have your stages, you start with vertex shader, which basically will take every vertex. It doesn't know yet about what you're gonna draw. It's like a bit, it's a point processor. So it doesn't know you're a triangle, it doesn't know you're a line. It's just like gonna process every point of your geometry independently. So this first stage is useful to do some form of displacement, but the problem is you can't really modify the geometry because it only knows about the point. So you can say, for example, move my point a little bit, or actually that's the stage which is used to normally transform to screen space. But you can't really modify the geometry itself. So once you go through the vertex shader, if you don't have geometry shader, then the primitive is that comes in the rasterization process, which will build the primitive. So when you have your topology here, like it will build the primitive depending on what topology you assign. So for example, point list means it will send a point inside the texture. Line list will means it will be segments. So every pair of points will be a segment. Line strip will be like it will take n points. It will take n points as a line. So it will consider, like if you have 5 points, it will make a line of, it will connect 0 to 1s, then 1 to 2s, and 2 to 3. And then you have, well, adjacency version, I'll go through that probably later. And triangle list is a list of triangles, so that means every 3 points will form a triangle. And triangle strip, I'll go through that one a bit because it's exactly in that example, so that's quite perfect. So then these primitives are formed and rendered and sent to the pixel shader. But in case you want to modify those, you have the geometry shader stage, which will then take the assembled primitive. So in that case, I receive a triangle, and you output another stream. So you say, I receive a triangle, and I will output other triangles. So that means you can output 0 triangle, you can output n triangles, and normally, yeah, you specify how much you expect to be the maximum here. So since some people did not do any yet, I will comment that. Okay, so in that case, and I'll of course put in wireframe. So that one is just a reference example, so that's just a geodesic sphere. So, and in that case, so if I go back through this one, so I have this vertex input structure, which now comes from vertex shader assembled. So it arrives as a triangle, so it says I already have 3 points. Then I say I want to output triangles again. So in that case, I say, oh, this is, I get position and normal, and append will be like, basically you say, append me a new point. So you append a new vertex. So here I take every point of the triangle and I append it again. So I just basically do pass through. So in that case, I would not need a geometry shader. But now the interesting part is you can completely modify those type of triangles. So if I say, for example, here, actually I have a mount here. Yes, it's open factor. So now we can start to modify our triangle. So we can just say, for example, P1 plus equal N1 multiplied by, like, E will be for extrude. So that's our extrude amount. So here we just gonna, because we're multiplying, we just scaling it, which is not really interesting. But now if we do something like sine p dot x, p1 here, and let's do ups. So now the problem is we're still displacing because the function is depending on the position here. So what we'll do, we'll also calculate the center, and instead of P1 we'll use center. So that means every triangle needs to be extruded from the same amount. So we need to get a reference point which is common to all of them. So here that's a simple extrude effect, which as you can see, it doesn't take much code to build a bit more advanced effect compared to what you have on Vertex shader. Like with very little amount of code, you can really do quite a lot actually. A lot of the examples in the workshop will be a bit like that. There's really little amount, but you can do quite. So that one is a simple extruder. And I'll just put a no curl here. I'll just. So yeah, we can have other example. Like for example, we can also, like in that case, I was only taking one triangle and moving the whole of it, but we can create more than one triangle. So we can say, now I received one triangle and I want to. I need the most useful feature, show cursor. Okay. So now we can see we want to create this type of ring. So to build this type of ring, we need to build, if I close it a bit more again, you can see 1, 2, 3, 4, 5, 6. So we need to build 6 triangle kind of per triangle. So so we have here, so we take our position on normal. In that case, we don't really use a normal except to push it back. We calculate our center. And what we will do is we say we calculate the 3 points which will go from our center. So one part is still the original one, and one part which is lerping with a factor value, which will mean take me a value in between the end of the triangle and the center. So we can build this type of. And we then append triangle here, triangle here, triangle here. So we can change this open factor by this I'll just put float amount equal E. And this is the same thing, like every value which is this form of reference, we can use any type of parameter. So you can use a texture sampling, you can use a lot of different type of values. So if I use the same here, no, it's my E value.
Wow, pretty secret.
So yeah, with really little amount, you can do all this type of geometries. So that you can also, so I'll keep that example. And you can also do versions of, you can also output nothing. That's also quite important. You can suddenly say, this triangle, I actually don't want it. So here. Yes, so if you don't append anything, you will have various error message. Also, it's kind of undocumented, but there's no DirectX11 compiler which does the same. So if you append nothing here, like the compiler will detect that you're pushing nothing ever anytime. So it will complain always in different ways. Sometimes it will work on Windows 10, on Windows 8, it will guarantee that it will never work. So you still need to provide a hint. So for example, what we will do here as another example, it's all, we will say, I'll just actually do something. I'll just copy it so it's a bit easier for you after the workshop, so you'll have a different patch for everything I've done. So when I'll give you back the material, that will be easier than going back in commented code. So I'll just copy paste example. So here. So now we had our example here. I'll just no, and I'll just clone. So here, now we have our version here. So instead of doing append like those, we can say something like if amount more than 0, for example. Or actually, I'll just put another variable, so float threshold. And get out of those also. And we need to get back that one, which was just pushing the triangle itself. So we will not extrude that time. Here. And we can change our threshold here. So now instead, so like the only difference from the previous one is instead of always pushing triangles, in that case we will say, okay, get the center, give me an arbitrary value, and if the value is not is lower than another one, then just ignore the triangle. So you can just suddenly say, oh, don't draw anything at all. So you can, but you have to still write something eventually. So the compiler doesn't allow you to just never write anything. You still have to say, in some case, I will write something. So yeah.
To safeguard it, would you do anything like else statement and then append a random?
Yeah, I have to do that sometime, which is really... Actually, on Windows 10, sometimes I don't, because the compiler no allows it, but on Win 8.1, you have to put some fake condition. But the compiler is actually really more clever than you sometimes. So if you put something like if 2 is greater than 1, for example, like that, actually, the Windows 10 one is not that clever because the Windows 8 one would actually detect that and will say, ah, no, actually, no, actually, it's the opposite. It's if 0. Yeah, actually, if I do if 0 is more than 1, then the compiler has just say, it's just going to get rid of the whole thing here because it finds, okay, it's a 0 greater than 1, so it's always false. So actually all this code is completely removed for you. So you see in that case, it will give you error saying, by the way, you're not pushing anything. So you still have to do something a bit conditional. So you say int I equals 0, idx, and if idx. So yeah, in that case, the compiler can't find the difference because obviously, IDX is provided by you, so it can change. So it can't guess in advance. So yeah, with GS, you can really do a ton of little effectors, like the ones you can see sometimes in 3D packages tend to have tons of those. And a lot of them are actually quite easy to do with geometry shader. It's not the fastest stage, it's actually by far the slowest stage. But it's a good compromise between, you can do those in compute, but it's much faster, but it's more complicated to set up. Or you can do it in CPU, which will still be much slower. So GS is a very good compromise of speed versus flexibility. So one thing also with GS is you can completely change the type of geometry. So here I'm receiving a triangle, but you can say, no, I don't want to push triangles anymore. I want to push a line, for example. So I'll do another example. So copy paste again. To line. To line. So now we have our same example, and now we input a triangle and we output a triangle. So now we can say instead, now I want to output a line. And I need a new one here also. So now it's appending, lines. And you can also do selection. So for example, we can do something like we want to output only the first segment of the triangle, for example. So we will do here append P1, N1, P. So you can do a lot of, like here you just say I want to output only one. So also it's a strip, so that means if you want to build a new segment, so like from here it will write this, and if I do P3, so it will write a new line. So that means you're beginning a line and you're appending a point. So you're building a path basically. So if you want to close the path and start a new one, you need gsout.restart strip. So that allows you to say, no, I want to start a new path.
Sorry, can you explain restart strip in more of a triangle scenario and stuff like that? It always confuses me a bit when you do like spline extrude shaders and stuff.
Yeah, so I'll just go, okay, I'll go through strip then, okay. So, yeah. So one first like this, and yeah, just I'll do one example to demonstrate it quickly. So yeah, you can see here I'm building a path, so I just first go from the first point, then I extrude, and then I go to another extruded point here. Oops. And let's say you want, I'll just do P3. Well, you can see every time I'm adding a new point to the path. So now if you do something like here and you restart strip here, you can see you're like restarting the path. So you're building this segment here and then you're building one segment here. So you just create two segments instead. In the first case, you create one segment, will be this one, then second segment, then three segments. So in that case, you will create three segments which follow each other. So that's the difference with strip in that case. So strip with triangle, yeah, it's a. I can explain those two, but I don't have much ready to go one. So I'll just, well, I just do a quick, I got example patches for it, but I will maybe do a mini drawing. No, that's probably 4V is not the best thing to do a drawing like this. I'll do that, something like that. Well, actually, I guess they really triangle. Yeah, I think they even have the drawing for once on MSDN, so it's easy to explain it graphically. Well, perfect. Yeah, if you have triangle list, basically the idea is you will have, well, yeah, it's not mega fast connection, so it's taking its time. Ah, perfect. Cool. So if you have triangle list, the idea is when you receive your list of vertex, every 3 vertex will be taken as an individual triangle. So that means if you have 0, 1, 2, 3, 4, 5, like this list, if you have a triangle list, it will do A, B, C, and D, E, F, because it's individual triangles. So that means in the case of triangle list, you will build 2 triangles, which is A, B, C, then the next 3, then the next 3. So with strip, it's a little different. So what it will do, the first 3 will be the initial triangle, and then it will use the 2 last plus the new one as a new triangle. So you can build strip like that. So for example, when you build geometry like segment, for example, or just a quad, for example, just a quad, instead of if you wanted to do it with a triangle list, you need to do A, B, C, and B, C, D as 2 triangles. So you need to use 6 vertex. Whereas if you do it as a strip, you can do A, B, C, and D, and you have your quad. So you can use only 4 vertices. So you can save a lot on memory by using strip, but it needs a bit more thinking ahead about how you build up your geometry upfront. So we'll continue anyways through GS quite a bit. Like the only, like with this example, the GS goes directly to pixel shader. So that means basically all the geometry we use, we can't really reuse it. So like if you want to say, oh, now I got this like nice geometry. Now I want to do another displacement on it. You always need to go through it. You just can't reuse. This goes directly to pixel shader and that's finished. So instead, you have this stage which is called stream out. And stream out allows you to say, oh, instead of sending my geometry to the pixel shader, you're going to send it to a buffer. So, and you can reuse that buffer as to draw it again. So you can pre-process, for example, if you need to render shadow maps, you can displace your geometry and reuse that geometry for every pass of the shadow. Because if you have shadow map, you need to re-render. So if you use shadow map, you would need to display this geometry once in the main render and once per shadow map. So that means you would have to do this displacement work several times, basically. Whereas here with stream out, you can say, oh, you can cache this result and reuse it later. So stream out has its own renderer, which is called renderer DirectX11 stream out. So that means you will say, oh, instead of rendering to a texture, I'm going to render to a buffer, basically. So it has different pins, which is vertex size. So that will be how much data you have for one vertex. Then it has element count, which will be the maximum amount of element. So if you go over that, you will have undefined. Normally, if you go over that, it will start to not do anything anymore. Like normally graphics card, if you go over, it will convert it to no operation. So it will just see, I'm outside of the value, so I will do nothing. And so enable this straightforward. View projection, we won't use it. Output draw mode will say, if you know the amount, fixed will say, draw exactly this element count. And auto means, I don't know how many triangles I will push in advance, so try to find it for me. Like behind the scenes, like draw auto. Basically behind the scenes, like if you use as auto, it will use this function. So it will draw auto will say, I get the stream out buffer as an internal counter, which you can access only through query, which is really annoying. So it will say how many elements have been written, but this number is only accessible through query, which is annoying. But if you use auto, it means it will say, oh, use the value in this counter, but it doesn't have to copy it back from the graphics card. So use the value from the counter and draw only this amount of elements. You can see it here. Refresh. If I say fixed, it will use the value here. So that means it will write 8,000 vertices. So some of them will be 0 value, so they will not be visible. But since I did not wrote as many elements, we can say, use the auto version. And auto version will make sure, I only wrote 120 primitives. So it will make sure you will send only in the next pass.
Is there any point in that stream out node apart from debugging?
Debugging, that's it, really. Well, if you need to write your geometry back also, if you need to save it you need to know how much is written. So in that case, you also need the query. But all queries are really all for debug. Queries are really just for that. So the main thing with stream out, like shader-wise, it's pretty much same thing. So, but the only difference is you don't have a pixel shader anymore because you're not rendering to texture anymore. And you have this construct which says, build me a geometry shader, but I need stream output support. So you say, I will not, you have to specifically tell, I will not render to the pixel shader. I want to render to a stream. So this one is just passing through vertices and multiplying by world. And you have to say here that's your, so you can have several stream out tools that I will explain later. So that means you can have up to 4 streams. So you can output to up to 4 streams. So that's each of them. So here we output to only 1 stream. And you have to specify the layout, which is this one, to say what are you outputting to which stream. So here you say, I output position, normal, and texture coordinate to this stream. And null, null, null means the other 3 streams are not active at all. And -1 means it's one of the, well, magic numbers from DX. It's like if you want to still use pixel shader, you could put to say, I want to send a stream to the pixel shader. But in case of stream out, we don't render to pixel shader, so we still have to explicitly say -1 to say we don't want to, we really want to ignore pixel shader. Like Nvidia card doesn't care about that one, but generally Intel, if you don't specify everything explicitly, Intel cards tends to complain a lot. So in that case, that's a really simple example which doesn't even use geometry shader because we don't need it. And we go from vertex, we process like, well, one bunch of blocks, and we just transform them by a matrix, and now we have only one geometry which contains all of our boxes. So that's one of the difference between using renderer stream out, you can use a standard layer pipeline, versus GSFX, which is one geometry as input, one geometry as output, which sometimes is quite limiting. With the stream out renderer, you can send a spread or geometry, or you can say, for example, you can do a group here and copy all this and remove that and do a sphere on top. And now you have one single buffer which contains all your geometries that you drawing all to a buffer. Instead of drawing everything, your scene to a texture, in that case you're just drawing your scene to a buffer. Render, this one is not, the advanced one is. So this one you render to a single buffer, but the advanced one, which has some examples later, this one is spreadable. So up to 4, because you have up to 4 stream out, so you can output to up to 4 buffer.
So you're saying if we do a GSFX instead of that, then we're limited to one entry, one output?
You can only have, it's one geometry in, one geometry out, yes. So you can't really do that type of operation in GSFX. In that case, it's really like you have a layer, so you have a scene, like as a layer scene concept, but instead of rendering to texture, you render all to buffer. So this whole buffer, for example, if I say I want to do a fong point, or whatever, and you can take this whole buffer here, group again. I just will not care about the order much, and let's translate it. So here in that case, you can see like so you processed all your scene, now you have a single geometry, and you can reuse that geometry in different cases. So if you take the previous examples with geometry shader, you can resend that geometry once to a guru with a transform, once to a form. So that shows you can completely reuse that geometry. So you don't process that renderer twice. You just process that once. It renders to the buffer, and then you just reuse that buffer once in guru, once in Fong. And if you want to, I don't know, if you want to redraw your scene several times, for example, now you can just replicate it several times again.
Could you do geometry instancing on that and still get like optimized performance and stuff like that?
It depends on the case. There's never one case which is identical. But you can, well, if you just, for this type of treatment, because they are really fast, it's probably not much faster to just do this instead of drawing everything individually. But if you quite start to have a heavy geometry shader or tessellation in the mix, for example, like if you use tessellation, you really want to cache the result because tessellation is expensive. So if you use tessellation in that part, it's a very big win in general to use streamout to cache the tessellated geometry. I have examples of tessellation later, so it would make some sense.
Is it useful for shadow mapping? Optimizing?
Yes, for example, if you do tessellation and shadow map, like you will not want to do tessellation once per shadow map, you would want to do tessellation once and then reapply this geometry on every shadow map.
But the font point still involves vertex shader? Or does it?
Yes, it's like, if you have to think, no, you have one geometry which contains everything. So you have one big buffer which contains your whole scene.
Yeah, but what about the font point? What does it in this case?
Well, it's like redraw. You can see it's redrawing the whole. If you start with your input here, so that's just some random box and a sphere. So instead, you would have to replicate everything. So now you have this one geometry, and you can see if you spread, like if you spread the input of the font point, you're actually spreading the whole scene.
Yeah, but it still runs the vertex shader, right?
Yes, yes, of course. Well, you run the vertex shader once per element of the scene. So yes, you still run the vertex shader, but in that case, the vertex shader will be simpler.
It runs the vertex shader in the font point. Therefore, all it does really, the stream out, is take all the points, bundle them, merge them together, and spit it out. And then in font point, it's another stage. It goes back to the vertex shader. Because once it goes out of stream out, the stages is finished. It's gone through. Do you know what I'm saying?
But there is still optimization, right?
Yeah, because you're always in the pipeline, right?
Yes. Yes, it's, well, the idea with streamout, if you do really simple work in the streamout, you will obviously waste your time because you will process this thing several times. But streamout is really useful in case you have some heavy workload. Like when you get heavy workload, you'll have, for example, if you have a really expensive vertex shader, like one of the two examples, well, there's tessellation, or otherwise if you have, for example, skinning, like skinning shaders tend to be quite expensive on vertex. So vertex shader will be pretty expensive for skinning. So instead of applying your skinning once in guru skinned and your skinning once in font point skinned, what you will do is you will apply your skinning in the process here. So you do all your blend skin, or well, skinning or blend weight are two examples of vertex heavy. And then once you arrive in guru directional or Fong, your geometry is already skinned. So you can keep your very minimal vertex shader, which is really fast. You can use that one. So you will do a small vertex shader twice and a big vertex shader once, which can be a win versus two vertex shader twice.
Yes.
So in this example, Because I'm picking up on Ned's point here, but it's a good point. Like, it is in the pipeline, but isn't it a bit slow because we got like haven't we got 2 passes? Yeah.
Well, you have to load balance, so sometimes that will be faster, sometimes that will be slower. As I said, like when you have vertex heavy, the extra pass becomes worth it because the 2 other pass becomes really fast. So you have to find there's a point where it makes sense and a point where it makes no sense. So simply put.
Thanks.
Well,
Yes?
if you want to put one color to the sphere and another color to the whole, to the spread of cube, is there an easy way to do it?
In that case, you will have to store the color as an attribute. So in that case, here,
You have to do it from there.
I can do it as example quickly. Okay, so I can do it. I'll just paste it again on clone so you can use it. So here, yes, okay. So here you have your list of boxes, and now what you need to do is you say you want color, so we need another attribute, so float for color 0, and we need to set the color, so float for color and now I need to store the color, so out.color equals color here. Oh. And so now you added, so I add the color of pair object here. Now we need to output it as an attribute. So now it's, so we just need to change the vertex to say now output me my color. And we need to set it here also in the output definition. Like here for now, it doesn't know we output color. So we need to tell, hey, by the way, I'm outputting color. And it's X, Y, Z. We want to output all 4 components of the color. So now the whole thing looks kind of mess because suddenly we need to change our buffer to accept color. So we need to add 16, like we have 4 channels, so we need to add 4 bytes, 4 by 4 elements. And we need to add, we need to change the output layout, and I don't think there is one example which has color here. So we will need to do, we'll need to do a join like this. And here we need, so we need to set the layout to match. So we need to set the layout to match the geometry. So I'll probably go again through input layout because I think. So for call row page and call row page here. So here now we say we had position, then we have normal, then we have texture coordinate, and we have now color. And we need to specify the format. So first, position is 3 channels, so it should be RGB2. Normal is 3 channels, so it should be RGB2 also. Texture coordinate is 2 channels, so it should be RG. And color is 4 channels, so that's so now we have a 4-channel output. So now we have the matching output, but the problem is the default Guru directional doesn't understand color yet. So we'll just do Guru directional vertex color. So we will clone the Guru, and in the input layout, whichever, is it texture, that one? Yes. We need to add again a float for color And I want it on texture only. So in this one, we need to put the attributes as input. And we need to pass, well, it's a guru, so we can just directly, let's say we'll just want to multiply. So multiply, oops. So input.color. And since my color is actually black here, and now if I do just HSL and I spread the color here, now every object, like the color is written onto every object, and now because the guru understands color, you have access to the color of every object from the previous pass, but you need to pass it around basically. So so you need one output, you need to set up your output, and you still need to change a little bit your shader so it understands it. Some of the default one could, but I don't think there's really any of the default shader which understands vertex color. So in that case, you need to write it. It's not very long to do, but it's still a mini task on top.
Okay. Right.
So you can set any attributes you want here, basically, and you can reuse. So if you want to, if you want to say, well, but in that case,
If you're using custom vertex attributes, is it all working exactly the same, or is there anything extra you need to take care of?
no, you don't have to. Well, basically, the attributes name, it's just you can put whatever you want. So yeah, maybe I really should explain that one. It's just there is conventions. Like people try to use the same type of naming. So for example, if you see position, you understand it's a position, but if you can really name it whatever you want. So if you want to call it hello, you can call it hello, but people will have a bit of issue understanding your code. But you, in the case you call it hello, you like in that case, this one is a simplified version. So there's an enum with the most common names. But then you need to put input element geometry advanced, and you need to put the fact that you provide here in the name. So you provide hello here. So if you have it, basically what happens is when the shader receives geometry, it needs to build something which is called input layout. So input layout is something which it's a bit of a contract between how you tell how you're gonna provide your data. So you say, for example, this is in which format I provide my data, and the pipeline will compare it with the input, what the vertex shader expects. So that's your vertex shader contract. So in that case, that means your vertex shader requires position, normal, and texture coordinate. If you have this as input, that means it's a requirement. Even if you do not use it inside the vertex shader, as long as it's in the input list, the compiler will never remove that. It will always be, this is what I need. So now in the input elements, you say, this is what I provide, and this is, for example, you can say, this is in this order. So you can say this is in this location, and if you don't provide any of those as missing, the construction will fail. Like the pipeline will say, well, sorry, but I can't do anything with your geometry because you don't provide what I need.
Like if you had a mesh with no UVs.
Exactly. I think if you have, I think icosphere doesn't have actually. Yes. Well, actually, because this one has vertex color, pretty much no standard geometry will be able to be sent to it, because no geometry has vertex color. So if I send a icosphere now, which only has position, normal, texture, coordinates, it doesn't have color. So when I'm connecting it here, it will look, and icosphere will say, I don't have vertex color. So actually, it will give error message. And here with reflection, we try to find what's missing. But that's not the pipeline providing that. The pipeline just give a random error message, and you have to, so it say I failed, but it doesn't really give you much information about it. So no, if it succeeds, I do nothing because it succeeds. But if it fails, I actually go reflect through all the input and I check. I try to match what's missing to give a meaningful error message, but it's not provided by pipeline.
So you're saying also that text coord 0, I kind of thought that it was a semantic that was given, like SV vertex ID, SV underscore anything.
SV are provided by system. So SV are reserved. That's provided by system automatically. So this one, you can't provide it yourself because it's a system which, it has internal counter. So actually it's kind of free as well because it already has internal counter to know where to look. So vertex ID is always provided by the pipeline. So all the SV are always pipeline, so you can't use them. You can put SV normal. Actually, it's not even. No, actually, SV prefix is forbidden. So SV is only for.
But so the text coord thing that everyone uses, that you see everywhere, is just a convention.
Yes, exactly. Actually, in some examples, I had the people using texture, which was super great because you have to go change everything everywhere. But yeah, so that's just really plain convention. You really put whatever you want, but with old pipeline times you had this naming, so this quite started to get a bit consistent, at least for vertex input, because for pixel shader, some people can use different type of attribute, because for example, if you want to say, that's not the right example, like if you want to say I want to provide something like, actually I really don't like that output names because it means nothing. Like it's not a texture coordinate, it's a view in normal space. So normally in many cases you can also call it normal's view. So some people do like that inside the pipeline, which make a bit more sense somehow. That is a bit like to keep with the old version, but I should really change to use something more meaningful because text coord 0, text coord 1 means a bit kind of nothing in that case. So yeah, and like this layout thing is also across stages needs to be valid. So for example, like when you have a vertex output and a pixel output, they also need to match. So like the vertex output and the pixel input will also be checked. So if the vertex output doesn't provide, if your vertex shader doesn't provide everything, at least everything that your vertex needs, then it will also fail. Sometimes on NVIDIA it works, most time you get a black screen, it also depends.
Did you say that you can provide the order?
Yeah, you have order of, you decide of the order and you need to always provide at least. So that means your pixel shader might only need position, but you can still provide position, normal, and texture coordinates as output of vertex. So as long as you have at least what's needed, you're okay.
Okay, and why you want to provide an order, a specific order?
You want to provide order because the idea is you always want to as closely match your vertex output to your pixel output. Because if it's perfectly matched, the pipeline just has to send it. If you start to change order, the pipeline has to think about it and do some work to be able to, to say, oh, I need to remove this attribute, or I need to take this attribute and move it in that location instead. So you give extra work. If you have a perfect match, your pipeline can just completely blindly copy. So yeah, the contract is also valid across stage. If you use fx, like in that case, normally the compiler will actually tell you. So I can do, an example. I'll call it mismatch error. I'll just take a constant here and clone mismatch here. So now here, I'll just get rid of as much as possible. Textured, this textured. So we don't need that anymore. We don't need that. Yeah, I'll just remove as much so to keep only the relevant part. So let's remove color transform this. So yeah, now for example, we have our pixel input. So in that case, our vertex outputs the same structure. So in that case, it's always the same. So you always have this perfect match. But now you totally allowed to do something PS input 2 and use PS input 2 as input of pixel shader. So now you're using a different structure, but because the semantic are matching, then the pipeline allows you to do that. So now if your vertex shader output, say I want to output UV as well, I'll just put 0 because it's not relevant. So now you can see, you have a different vertex shader output and a different pixel shader output. But because everything that your pixel shader needs is present here, then the pipeline will just say, oh, well, text coord is not needed, so it will just discard it. It's still calculated by your vertex shader, but the pipeline will discard it at some point. But now, as a difference, if you say, oh, now I want to have a color input in pixel shader, so if you float for color.color, now you see you have this error message. You'd say, I can't find a combination that works, because now you say, oh, basically your pixel shader say, I'm expecting color, and the vertex shader doesn't provide color, so it can't really invent color. So it's I have no idea what to do. Actually, some cards sometimes give a black color, some you can have a crash, so it can be quite variable. So you need to always provide at least. And yeah, even if the color is not used in the pixel shader, it's still marked as I need a color. So the pipeline doesn't know necessarily it's not going to be used. So even if you don't use it, you still need to provide it. So that's for the first part of the basic stream out, but now we're going to start a bit more advanced version, and I think advanced stream out will probably will be just fine for lunch, just before lunchtime. So yeah, with the GSFX, you have only one geometry in, one geometry out. With the stream out renderer, you can use your whole layer pipeline, but you have only one buffer as output. So now, sometimes you might want to have several buffers as output. So if I take, for example, back this, I think that will be this example, actually. That's not the first example. But for example, if you had this decimate version, which was saying, if you over this value only output the triangle, you could say, if you over output to this geometry, and if you under output to this geometry. That's the next example. So this one is renderer stream out advanced. So it has it has a couple of differences. Well, the first one is obviously buffer count, because now you can output to several. You want to say, I want to output to multiple buffer. So it's your valid value is between 1 and 4. But if you put 16, it will automatically be clumped to 4. So it will at least try to not crash. So here, idea is we need 3 buffers. Then you have vertex size, which is the same, but no. Like the idea is we have this box which have position, normal, texture, coordinate, and the idea of this shader, it will say now every attribute will be pushed in a different buffer. So now you will have the first buffer will contain only position, the second buffer will contain only normals, and the third buffer will contain only texture coordinates. So instead of having one buffer with all the data inside, you'll have one buffer with one particular set of data inside. So vertex size now, because we have 3 buffer, I kept it as manual here. So like 3 float will be 12, so it's 3 by 4. 3 elements XYZ by 4 is 12, 12 and 8. And you have input element here. So you say I want to output position, normal, texture, coordinate. And you have your maximum element count and eventually draw automatically. So as output, you have this geometry out, which we will not use in that case. You have geometry slices out. So geometry out is, in that case, they are the same. So it's like it's like output geometry slice. So every buffer, like first one will be position, second one will contain normals, and third one will contain texture, coordinate, and it will be one geometry which will draw one of them per vertex. And geometry slices out is, in that case, it's exactly the same. Like there's cases where it's different, that's for next examples. And then you have buffer out, which are byte address buffer. So instead of attaching those as geometry, you can attach those directly as buffer, so you can read them in vertex shader or compute shader. You can read them in different pipeline. Like if you have it as geometry, it will be provided as vertex. So every point of your vertex will be, you have to get this one. Whereas with byte address, you can access any vertex anywhere, for example. So it's more for compute usage. So in that case, the first thing we need to do is we need to split those buffers. So now we are set up. We say we have 3 buffers, we have the right size, we have the right amount of elements-ish. And like you have this one, which is called attach index buffer for next example when it's going to be different. And you have binding, which is for next, so it's hidden for now. So now we say we want to draw only per point because we want to draw per vertex because we just want to re-output the vertices. So the split buffer is actually doing nothing. That's what's quite pretty amazing. So you have your vertex input, so position, normal, texture, coordinate, and you say just return vertex shader, just say return itself. The only difference is now when you build your binding on stream out stage, you have this here, this little difference, which is the buffer index. So that means here you say in the position part of my output, I want it in buffer 0. Like the normal section, I want it in the second buffer. The texture coordinate section, I want it into the third buffer. So you can, in the output, you don't only assign like what you have, you really also do routing. So you say where you want it to write it. So if you want to, and you can really do like any stupid fine-tuned thing you want. So for example, you can, I'll just copy that one. You can say, as long as I want to output position XYZ in buffer 0, and I want to also output it in buffer 1. So if I say draw me that's position, that's normal. You can change all of your routing basically. So you can say I want only XY of normal here and 1 dot position dot x. So you can quite change everything.
Hang on, you can push more than one through.
Yes.
Wow. What happens? How does the data get?
It tries to figure it out, but it's very rare to use that type of scenario, but you can, yes. So normally here it should try to put XY then X, so it will do 2 components of normal and then 1 component of position. So you can really route anything you want, whichever way you want. And later for multi-stream, you can do it also per stream. So you can have different streams that push in various buffers. But so idea is you just have here the buffer index, so position normal.
So you can actually have multiple streams, but each one can have lots of buffers.
Yes, you can say one stream contains texture, coordinate, and color, and another buffer contains only normal, and one buffer only position. You can really decide and fine-tune any way you want. You will use your input element to design it after for the drawing, because in case of byte address, it doesn't care, because it's just a buffer, so you interpret it the way you want. You don't need layout, but to redraw as geometry, you need a layout, of course. So idea here, well, to just see it, well, one of the main uses, if you want to reuse this in compute shader, for example, using multiple buffer makes it much more convenient, because instead of always having to use this tried input to know where is this element, you just have your float, it's 12, so you can always output a position of 12 elements. So that's like this one draws as byte address. So if you had one, like here you have one buffer, so that means actually when I want to get position, I do a load of like vertex ID multiplied by 12. So actually here I only use vertex ID, so I only attach the box for the index buffer. But all the vertices are picked up inside the vertex shader instead.
Sorry, just because you mentioned what this was good for, is there any other real reason for doing this than having a really tidy, as you said, split your position and normal into a...
Well, having it tidy is already a good step, I think. So it's quite a very good reason for my test.
Is there
You have another thing, it's also, it can be quite much more efficient.
Right.
Because you have that, for example, if you don't, in that case, actually that case is a very good example, because here I only want to display position, so I don't use neither normal and I don't use texture coordinates. So instead of having one big buffer on the pipeline to have to kind of find a bit where it is, it's more cache friendly basically. So the read will be much faster if you only provide a buffer, because you have contiguous data. So your data is packed together, whereas if you have a single buffer, your data is like a bit split. So you have a bit of this, then the pipeline needs to split something, then get something, then split something. And obviously even this fact of ignoring something is not free. It's actually quite very expensive sometimes. So it's also faster in general to have multiple buffers.
And am I smelling vaguely some use case with deferred rendering, or I'm getting ahead of myself there?
Not necessarily. Well, if you have shadow maps, it's the same. If you read only the data you need, or sometimes just discard, if you need only position, but you're going to need it a lot, you can just process once to get rid of everything and just get position and use it several times. And so yeah, of course, if you say here input dot pos multiply equal to, yeah, obviously if I change it inside the stream out, it's this one is reusing what's in there. So we can see like anything we change here will be obviously sent to that one. So yeah, the only difference is instead you just have, because you only have the data, you have like, you load like as IV multiplied by 12. So you say my byte address buffer is just a bunch of bytes. So you load 3, it only understands int. So you load multiply by 12, which is the size of 3 float. And you have to use as float, which is a cast, like for people who do C#, it's like a binary cast. So we'll say, oh, this is binary data as float, so please interpret it as float. So if you were using packed data, you would always have to use a stride equal int stride equal 24. And for example, if you have only position normal, you'll have to do that. So you have IV, then you need to put it in here. If you change your layout, you need to obviously change your stride. So you always have to reinterpret your data when you have packed data. Whereas here, because it's separate buffer, you just can easily say, oh, just read me. The only thing which is annoying is you have to use byte address, because ideally you would want to use structured buffer float 3. But the problem is the pipeline DX11 doesn't allow that. So as soon as you have a structured buffer, you can't be attached to stream out. It's not allowed. Because instead of you could, if it was possible, that would be the most convenient, because then it's just like treated as an array of float directly. You don't even do those loads, but as stream output, you are not allowed to use structured buffer. I don't know why there's this limitation, but it's there.
So would it be faster having DirectX?
No, it's the same thing. Anyway, when you use a structured buffer, internally the pipeline exactly does this load 3 and does the casting. So it's just you write it manually. But speed-wise, it's pretty much same thing to use structured or byte address. It's just more convenient to use structured in general, because it's a bit, well, it's a bit more convenient to think as an array of elements instead of thinking as a bunch of binary data. So yeah, well, one of the useful things when you have those buffers is they obviously suddenly really easy to save. So you can say, for example, I want to save my position. So you say float 3 here, 12, and get slice. Yeah, so if you want to save only some parts of the data, it's the same. Instead of having a read back, which would be float 3, float 2. Instead of having buffer, which would have to get rid of that data if you need position only, in that case you have much less, you provide much less work, so it's much more efficient that way. And it's more convenient because for the same reason, especially in that case, if for example I add a color attribute here, I can still read back my position. I don't need to change anything here. Whereas in the case of this readback, if I add color, I still need to go to inspector. So if I want to do something dynamic, then I just can't, because you have this config pin. So you have to do a bit of weird set patch thing, which is never so recommended. So here it also allows you to really get only what you need, which is. So yeah, this one just shows as debug. So here I just have one technique which picks from position buffer. One technique picks from this one picks, well, I always need to pick from position buffer because I need to draw the object. But this one will say output color as normal, and this one will say output texture coordinates. So I have different load here. And you don't have, yeah, there's no need to juggle with any of these stride things. So yes, like the split is really useful for compute in general. Like if you start to do mixed mode pipeline, it really simplifies the process quite a lot. So one thing which we can do, so I'm kind of for this one, if you're on ATI, I'm a bit sorry, I'm not sure this one will work. I really normally try to have things working for every card and I try to test it, but this one, I just could not yet. So as soon as I find a ATI working, but if you're on NVIDIA, you should be okay.
I had a question about the previous patch you did.
Yes?
So would it be redundant to have an MRT under the stream out if you were actually going to do deferred rendering, or would you use the buffers directly?
No, if you need to use it only once and you don't do any work, stream out is completely pointless. Like if you do a very little work, which is transform vertex and push texture coordinates and normals.
Let's say you had a really heavy GS, and then you want to do deferred rendering.
If you have a very fat GS, well, if you do shadow, if you need to do geometry twice for deferred, normally, if you don't do shadow, you can only push geometry once. Then in that case, you don't, because anyway, you will push your geometry only once, so you will not need that. But if you start to do depth pre-pass or shadow map, as soon as you start to use your geometry several times, then at some point it might become faster, but it's case per case scenario. I can't give an exact answer. Like the cost of doing the stream out will have an initial cost, obviously, because you need to do another buffer and you still need to render twice. So if the cost of the stream out outweighs after the cost of doing your GS twice, then it's a win. But that's something you need to do on a case by case basis. Generally, if you have tessellation on a heavy GS, it's quite common that it will be a win, though. So now one thing which is also possible with streamout is like streamout buffer are not usable as vertex, but they are usable as index. So one problem we often have with standard streamout is you output vertex geometry, which is a very big problem. Because when you have vertex geometry, you lose index buffer. So that means you lose a connection between vertices. But with streamout, you can also build an index buffer. So, well, who exactly don't know how index buffer work exactly? Raise hand. So everyone really knows how index buffer works?
I highly doubt it. No offense, though. No, just was saying that I doubt it.
Yes.
Everybody knows that.
Okay, so index buffer is roughly a lookup table. So when you have all your vertices, so instead, like for example, if you have a quad, you'll have 4 points. So you have 4 vertices, but you have 2 triangles, so you need to draw 6 points at some point. Because, well, I'll just put a quad constant. And a wireframe. And so, well, it's kinda and magic toggle. So yeah, well, it's gonna be very easy to understand with a quad. Just idea of your quad, you have 4 points here, but for drawing a triangle, you still need 1, 2, 3, 1, 2, 3. So you need to draw 6 points. Sometime in the pipeline, you will have to use 2 triangles. So 2 triangles need 6 points. So what you can do when you build your geometry, you can do it per vertex. So you can replicate your vertex. So you say, I have triangle 0, triangle 1 on vertex 2. Then you say that's vertex 3 again, that's vertex 4, and that's vertex 5. So you have you have like 6 vertices, but those 2 are exactly the same. But if you have position, normal, texture, coordinate, all this data is replicated every time. If you start to have like a grid, like just doing 4 by 4 grid, you can see this point is actually shared quite a lot. So that means in that case, this point is replicated 1, 2, 3, 4, 5, 6. So you have this point is replicated 6 times, which is quite a lot. So instead of replicating those buffer, you say you put only those points only once. So you have, it's like you have an array or a spread of vertex, and then you have a spread of int, which is the index buffer, which is a get slice, basically. If I want to think of index buffer and vertex buffer in 4v terms, your vertex buffer is just a spread, and then your index buffer will be a get slice. So it's a spread of int, which will be the location of the vertex. So you will have a spread of int, which will be a get slice in the vertex buffer. So instead of building that point like 6 times, you will build that point only once, and then the index buffer will be 0, 1, 2, 1, 2, 3. So it will just, instead, it will be 12 bytes instead of 32. So you already, if you have position, normal, texture coordinates, you have 32 bytes. If you have an index table, you have only 12. So you're almost saving 3 times the memory, which is, well, if you start to work with very large 3D models, that's very big performance game. Like every 3D engine use index buffer, basically.
And so the internal counter for the vertex shader is equal to
Vertex ID. Yes. So it's only, you only process the vertex once in vertex shader, even if it's shared several times.
So sorry, you're saying that my index buffer may have, so the index buffer count is bigger than the vertex count?
It depends. You can have a smaller index buffer if you want also. There's cases.
So you're saying the vertex shader takes into account the vertex count, not the actual index buffer count?
The vertex shader only doesn't know about index buffer, actually. The vertex shader only knows about vertex, and it doesn't even know if you're triangle. It doesn't, because index buffer is also used to assemble the primitive depending on topology. So, like the vertex shader doesn't know anything about that yet. So what it will do, it will process 1, 2, 3, 4, 5, 6, 7, 8. It will process 16 points independently, basically. And then once it's processed by vertex, this modified vertex will be assembled using this index buffer. So you can't really modify index buffer in the pipeline. Well, like geometry shader would eventually have access to some info about it, but that's it. If you want to access actually the, you actually can access index. If you want to access index buffer data, you could have you can pass the vertex ID as input to the geometry shader. And inside the triangle, you will have the 3 indices, which will be what was in your index buffer originally. So that's the only way to read index buffer. It's a bit of a hack. You don't really read it directly. You need to pass this data around. So, well, one thing which is very useful for shared vertex is also they are shared. So that means you can have smooth normals, for example. So if you want to calculate, if you modify your vertex, you need to replicate the normals, and you lost all connection information. So once you have index buffer, you can start to write shader which says from this point, I want to know all the neighbors indexed. When you don't have the indexed buffer, you can't do that anymore. So one thing you can do in GS, you can write anything to a buffer. So that means you can, in that case, we just actually building the grid node. So it's basically this thing is exactly the same thing as the grid node, but it's done in shader instead. So, well, it's not a really huge case, but if you start to have a 64 by 64 grid and you want to modify it a lot, obviously it will be faster to build that type of things in the graphics card instead than to, like the grid here is built on CPU, so every time you modify the size, you're rebuilding the grid in CPU. So if you, for some other type of geometry, if you want to modify the parameters a lot, you might probably prefer to write it in shader because it will obviously be faster. So how is it working? So now the stream out is a little bit the same. So now you can also start to assign a bit more complicated scenario. So in that case, we'll have a 2 buffer output. So the first output will be the vertex buffer. We will not split the vertex buffer. In that case, it's only the vertex information. And the second buffer will be actually the index buffer. So we will write the index buffer in a geometry shader. Well, actually in a vertex shader in that case. But. So also one thing in that case, you can set vertex size to 0. If you set vertex size to 0 or negative number, it will automatically pick up from the input layout. So instead of having to calculate by hand, it can interpret 0. So 0 will mean, I know the size because I can pick it from here. So you can set it by hand. If you set it by hand, it will pick the number you say. But you can also say 0. So in that case, it would, I know its position, normal, texture, coordinates, so I can do it myself.
What is binding?
So binding is the next part. 1 second. So in that case, also now we don't want to draw the geometry individually. What we want is we want to use one of the output as index buffer. So we want to say one of the input of our geometry, I want one of the output, like one of the buffer as vertex buffer and other output as index buffer. So the geometry slice count is still 2, 1 buffer. Actually, if we read back here, the first one will be float 3, float 3, float 2. Well, we need to read it from here, get slice. Node. Row, please. Buffer in oops. Row, please. Okay, so this one is, well, basically it's where if you will do a position split, so you have the position, normal, texture, coordinate, but now you can get slice the other one, which in that case is going to be int, well, oops, I'll do it 3 times. Yeah, on this you can see the indices of the grid. So one buffer contains indices, one buffer contains vertices. So idea to build the grid, well, you have this null geometry, which is, well, people don't know about null geometry? Who doesn't know about null? So null geometry will just say to the pipeline, draw nothing, so you will only use vertex ID. So in that case, we want to generate the geometry. So that means we don't have input geometry. So we just tell to build the vertices. We just say I want to build points, and I want to build a grid of 16 by 16. So I need to draw 256 points. So in the grid here, so you have one technique which will build the vertex buffer. So basically we get vertex ID, which will be a number between 0 and 256. And since we have our grid, like our row count and column count, we use modulo operator to calculate the row index and modulo operator to calculate the colon index. And from that, we can calculate the texture coordinates. And from the texture coordinates, we can calculate the position. So that's how you build a grid in Vertex shader, basically. The only problem is this only builds the point. It doesn't build the connection. So yeah, also if you don't want a grid, you can start to process that type of geometry. So you can say pos equals sphere uv dot. Well, you can display that grid also. So I just do it simple. Pos dot x plus equal uv dot x. Maybe z. Okay. I didn't have this. So you can also display the grid. So instead of using one on displacing in Vertex shader, you're building a displaced grid from scratch. Actually, that's a good. That's why. Oops. Anim equals 0 and plus anim. So yeah, here you're rebuilding your grid every frame. So if you were doing those in CPU, obviously you would have to redo a big buffer every time. So you can build, if you need to build it only once, obviously the grid example makes no sense. But if your geometry needs to be animated every frame, then it starts to make a lot of sense because you build it directly in the graphics card. So you have one first pass, which is building vertex then. So it's like taking modulo operator. And now we need to build indices. So that one is a bit more complicated. I'll stop animating. And I'll just put back to 0. So now we need to build the connection. So the connection, here what we're gonna say, we're gonna output two triangles at the same time because it's more, we're outputting quads basically. So now to build the index buffer, here you have, if you look at the mouse, you have 0, 1, 2, 3. So vertex buffer is built that way, 0, 1, 2, 3, 4, 5. So up to 16, and that's number 16. So now to build the triangle, we need 0 and 1. And we need to go one row up. So we need to say, we need to grab the modulo again. So 0, 1. And from this 0, 1, we need to go up 1. So we go to 16. So that one is building like a really index buffer. So now you really have index geometry and you can reuse it. Eventually, if you need your geometry once, but you can also speed up load time because if you do it in CPU, it will take some time. But even if you build it once, you can build it only, you can do it and just disable after. So it will preserve the geometry if obviously if the renderer is disabled. So yeah, what it does, that's why you need to say, now you have to also say, so you have the first pass, which builds vertex buffer. You can actually see, if you don't put the 1, 2 dots, it defaults to 0. So here I did not put it. So I say the technique for vertices outputs position normal text chord to buffer number 0. And we can see in the technique index to generate indices, then we output to buffer number 1, obviously, because we need to have 2 different buffers, one for vertex and one for index. So now the problem is if we have to say, oh, now we want to use the vertex buffer with index buffer. That's why you have this toggle, which will say, I want to attach an index buffer. As soon as you put this toggle on, this geometry will become indexed instead of per vertex. So if this toggle is off, this geometry will always be buffer 0 and buffer 1. But in that case, you see you have only one slice. And you have to specify the binding. So that means here you say, I want to use buffer 0 as vertex buffer, and I want to use buffer 1 as index buffer. So if you wanted to reverse the write, you could say, or you could also split buffer, so you have a limit of 4. So you could say buffer 0 is position, normal, and texture coordinate, and then you attach all of this to your index buffer at the end. So yeah, the large advantage with index is it's just much faster to process. So if you can build indexed geometry instead of vertex geometry, it's generally always much more efficient.
So you're saying we should do this whenever we don't have an index.
If you can put an index, if your geometry can be done as indexed, it's always much better. Yes. So for things like grid, you can go through quite a lot of primitive because cylinder is just more or less a displaced grid if you want to think about it. Actually, I can totally do that one.
Go on, make a cylinder. Draw a cylinder. Draw a sheet.
Oh.
Draw a sheet. You know, something to very
Ah.
the little prints. You can draw me a sheet. Talking to everyone, bro. My God, get the references.
Oh, it decided to unconnect everything, obviously. That's great. I just grab the example because shader got broken. Okay. Yeah. Okay, so
Yeah, kids, Vox knows the cylinder equation by heart.
yeah, I don't really know it by heart actually. I was okay. Give me a little sec. I should even do it. Or do I do something different? Huh? Oh. Quite slow today. Ah, hang on.
Pause does it.
No, yes, sorry. Yeah, it's pause.z indeed. Yes, good point here. It's not very cylindrical yet.
The cosine of UVX, not UVY.
Huh?
Yeah,
Ah, yes. No. Well, I'll redo that one a little later anyway. Well, I'll go back through this one a bit, but yeah. So yeah, you can quite displace. Well, you can use height map also, of course. So if I take a Perlin, texture FX, preview. Okay, and this one will go back. And I'll get a constant. Okay, so now we attach our texture and pos.z equals input texture dot sample level. That's linear. Ampla UV 0. And here, yeah, I can get red only. No, it's not really wanting to be happy right now. Ah. Okay, go back to that. It's not outputting anything somehow. Yes? Ah, stupid, thanks. Yeah, there we go. Thank you, I missed that one.
Nice one.
Yeah. And well, actually in this case, one thing which is quite useful to do is we do xz on pos y. Because generally when we do height map, we just want xy. So the grid, it's always a pain to do it with a rotate or something like this. So because here you generate the geometry, changing the plane is kind of really straightforward. So here that, yeah. And let's. So here, yeah, you built, well, height map, which is quite convenient, and because if you need animated, if you animate your Perlin on your height map, you can build your geometry every frame, and this method will be really fast. So instead of even take a grid and displace it, you can go one step further and just build the grid from scratch every frame.
sorry, that's faster than any vertex shader displacement or something like that.
Well, you still run vertex shader, but you don't have to fetch things around. You can build only what you need. If you don't want normals, you just ignore them. So you have a bit more freedom. You're building geometry from scratch, so you have full freedom on what you want to do or not to do. I mean, it will run vertex shader, so it will be speed also.
I have one question. So when you're doing like a displacement on the vertices,
Yes.
do you have a concept or like a suggestion of how to recompute the normals?
Well, there's two ways to recompute the normals. Well, you can, if you have access to gradient, basically you can use a small step, like a bit what people do in remark. So you do that gradient based, so it's called central difference. In some case, if you use some form of other formula, if you can, it's better to have, if you have derivative, then you could use also derivative instead. So you can do the derivative on x of the grid, so instead of building your formula 3 times, you can use derivative, because most of the time you can reuse intermediate, but I don't think I got example by hand here. I'm sure I have one on the drive, but I'll look at it for lunch. I'm sure I can find it, but it will take some time around here. So I'll show it. So yeah, you can build this, or the third option is, because it's indexed geometry, what you can do in compute, you can take this index buffer and build a vertex neighbor. So you can say for each vertex, you build a big list of every vertex connected. You can say, you can know every triangle that this vertex is connected to. So you know this.
But the new position of the vertex will not be available, or like only next to.
If I take back the grid quickly, it will be easier to explain. Here, like I know, and that should be default. Magic show cursor again. Like you know this, I'll do, let's redo, I just use a standard grid that will be the same because I want lower res. 4 and 4. So now you have this information of triangles, so you can also process this index buffer in compute. And you can say, for example, for all, you build a list basically. So you can say, vertex number 0 is part of triangle number 0 and triangle number 1 and triangle number 2.
But then you have to recompute basically the normals as a
Yes.
second pass.
Yes, you have to. You can't do it in one pass. You have to do 3 passes. Basically, you have to do 1 pass to build the geometry and displace it. You have to do a pass where you build the neighbors. But even though if it's a grid, the index buffer and the table are the same. And then from that, you can do a sum of all normals. You do flat normals of every triangle, and you do a sum of them, and you do an average of them. I got an example of those somewhere too, but that one, it's quite hard to do. You do it in compute in general, so it's a bit tricky to do in standard pipeline. I think you can even do it for normal. You can even do it without the table. You can quite accumulate normals somehow. You can. I'm sure I can find it. So.
Okay,
But so yeah, you have 3 ways to do normal. So you do the central difference, you do table, or you do a derivative. So yeah, and well, if you, that's one is just to show as a little cleanup. It's just instead of having 2 shaders directly, you can just do 2 pass directly. It's quite allowed now. So you're allowed to do multi-pass in DX. The only thing is your vertex input needs to be the same for every pass. That's the only limitation you have now. But otherwise, you can put several passes. So instead of doing a group with the shaders, that's just a quick version to make it all in one go. So you have first pass do vertex and second pass do index. So you just have one single shader instead, which is, well, always nicer for matter of cleanliness. But function-wise, it's exactly the same as if you did a group, basically. And, okay, well, 15 minutes. Well, I guess that will be just enough to show this last example for the morning part. Yeah, so the thing is, yeah, with multiple stream out, well, for the moment we've been pushing to several buffers, but we always had only one stream. But with stream out, you can also have up to 4 buffers, and you can have up to 4 streams as well. So that means you can start to build you can start to assign a stream to a buffer. So if we take the example of this decimate one previously, where you say, oh, I want to basically anything which was below this value. In that case, I just use a y value. So anything which is below a y level is discarded. But what sometimes we want to do is we would like to do anything which is below this value, I want it in one buffer, and anything which is above this value, I want it in another buffer. So what you could do is you can do 2 stream out, and then have 2 techniques and 2 passes. One pass outputs to buffer higher, and one pass inverse the condition and outputs to the other buffer. So you could do a 2-pass version, but well, instead you can also do a 1-pass version. So instead, if you have advanced stream out, now you can start to say you can have multiple stream also. So before, every geometry shader example from before had only one single in-out stream, but you can actually have up to 4 of them. The only thing is when you have more than one, you must output point stream. You are not allowed to output primitives. But in that case, because we want to reuse geometry later, it does not matter.
And so we replace the triple null. Alright, yeah, sorry.
Yes, so now instead you have the first stream has position normal, and the second stream also has position normal, exactly the same. But now you say the first stream outputs to buffer 0, and the second stream outputs to buffer number 1. And so now you can just say, well, take your full triangle, we calculate the center of the triangle, and we say if the y of the center is below a certain level, push to the first stream, otherwise push to the second stream. So now as output we have 2 buffers. We have one buffer of everything below and one buffer of everything above. And you can do it for a whole scene as well. So you can suddenly say, oh, everything below I want to render it with Guru and to render it as a solid. But anything which is above, I want to render it with constant, and I want to render it wireframe. So you can do with all the displacement you can do on top with GS, you can do really tons of funky effects with that type of thing.
So it's just whatever order they're declared, and will automatically be indexed.
Yeah, order of declaration will be order of the stream here. So if you say normally 1, 1, and 0, 0, it will just reverse which buffer it's outputting. So in that case, it's reversing the condition. I'm not
sure there'd be a reason for this, but could you do 0, 1?
You can, yes, I think that's normally completely allowed. You can do something like that. In that case, it makes kinda not much sense, if I remember right.
What do we have? Sorry, man. It's just the unroll shit really fucked me up.
Unroll, you basically means if you say unroll, you try to tell the compiler, I want you to do this instead.
That's cool. I get it.
That's exactly what you ask the compiler to do. Yeah. So instead of doing it by hand, you ask the compiler, try to do it. But in the case actually you put a fixed number here, the compiler will do it anyway. But generally I try to put it because it clarifies intent. Like the compiler will do it, so even if I don't put it, the compiled code will be exactly 100% the same. But because it's a bit documentation, I could just put a comment, I want to unroll, please. I know it will be unrolled, but it just shows the intent.
But I think, sorry, I once came across this problem really with doing texture sampling within the loop with sample. Yeah.
Yeah, it can't unroll anymore because you depend on a condition.
Right.
Like here, you don't depend on a condition because you go from 0 to 3 all the time. If I start to just put something like int iter equals 3, if I replace the I by iter, then obviously the compiler can't know the value of iter, so it's not capable of unrolling the loop anymore.
Right, I get it. Thank you so much. That's why the error message was, can't unroll.
Yes, it says I can't do it because I don't know the number exactly.
Okay, thanks. Okay, what a bitch.
So yeah, you can obviously extreme, you can do different things. So you can say, no, I want to extrude the first stream, for example. So we will say input y dot plus equal input y dot norm. Is it norm? Yes, norm. Multiply by sim dot x. That will do. And let's multiply frequency. That's probably not the best. I'll do it on the other one actually. So you can apply all the effector on top, of course, as well. But generally, you don't really want to do those. You prefer to do it as different paths. So you can say, for example, if you can say, oh, I want to extrude only the part on top. Now you have two buffers, so it becomes really straightforward. If you have some of the GSFX that does this type of extrusion, I think there's a bunch of country, but I think you have them in noodles anyway, probably. So you can suddenly put it with noodles and say, oh, do me a displacement. You can say, oh, the bottom part, do me this type of displacement, and the up part, do me this part of displacement. So with this type of splitting, this becomes really straightforward. I guess I'm sure you will make a module of it soon.
Make like a nice selection.
Yes. And you can do any form of selection you want. I took XY, obviously, but you can say, for example,
You can even do index count or whatever.
you can really do anything you want. Anything that returns true or false is a candidate for it, basically. So if you say, for example, if you want to do it as a float 4 plane, and float SD plane equals float 3 P. That will be a return dot p plane dot xyz, and I always forgot if it's plus or minus, so I will see. Well, something like that anyway. P. Plane dot w. Sorry. Yeah. So now instead of the condition here, we can do if SD plane CE lower than 0.0f. And now we have our plane, so that's our plane normal. So we have here we have a plane that goes up, but now we can let's do Cartesian. Vector, please, and XYZW should be here. Perfect. So now you can do like more like plane-ish slicing. So it's just another example. There's a more complicated example of plane slicing, but that will be for after lunch probably.
Secret.
But so yeah, you can put basically really any condition you want. So if you want to say, I don't know, anything within a sphere, actually distance, for example, distance function, like same as you use for remark distance field, are really straightforward for this type. So if you do SD float for sphere, oops, and SD sphere, and that's going to be distance instead. And I want sphere here instead. And if we replace it by a sphere function, now it's like instead of having a like straight line, if I increase the resolution, it probably will be a bit more visible. And that sphere here. So depending, now instead of using distance from a plane, we use distance from a sphere. But we can really use anything we want, and you can do a bit of, you can do some more advanced geometry selection. But the big advantage is all in one pass. You can also build what's passed the test and what kind of fails the test. So
you can do kind of remarching Boolean operation with this.
Not really, because with plane, I'll explain.
So I didn't mean with the sign distance field and stuff like that,
Yeah.
but more like, well, yeah, with sign distance. I didn't use the SD sphere function, and then you put that around a like really highly defined box, and then that's how you could have real-time Boolean operation, no?
Yes and no, because one of the problem is like with plane, it's really easy to split triangles. That's something I explained this afternoon. It's really straightforward. Well, it's, let's say, straightforward enough to do it with a plane, but to slice with a sphere, you need to make decision on resolution. So it makes the whole thing really much more complicated. So yeah, that's pretty much the same, same code. But yeah, with all the stream out on the pipeline setup, even with not so much code, we can really do like really tons. It's not like we need the mega complicated 1,000 line of code shaders with really, really small things. There's a lot of way to do it also. So I think, yeah, I think it's 1 p.m. No? So maybe we do lunch. I think it's 1 p.m. So we might do lunch. Yeah, because I think after, well, there's quite still. Yeah, there's still some heavy program to keep you entertained for the afternoon, I guess, anyway.